In this video, we're going to look at part B of example 1 in section 8.6 on power series. So what we're going to do now in part B is look at this series, so the sum of infinite terms that we were looking at in part A. And we're going to determine for which values of x does this series converge. So when do we get, for which x's rather, do we get a number for this sum? Do we converge? Okay, so that's the question of part B. Then we'll look more into the specific values of, or the degrees of our Taylor polynomials that match the function. So first, just convergence of this infinite series. All right, so let's recall from our previous work in this chapter, when we were looking at whether or not a series converged, we had a list of different convergence tests that we could use. One such test that's going to be helpful here is the ratio test. And as we go through this, you'll see maybe why I chose that test. Maybe I'll just say right away, you'll probably notice that these terms in my series look like this: 2 to the n, x to the n over n factorial. And typically when we had an n factorial there in the denominator of a series, or the denominator of terms in our series, we'd use the ratio test. So let's just set up this test and see what kind of information it gives us. All right. So recall the ratio test, we considered the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Okay, so what is a in our case, or a sub n? Well, a sub n are just the terms in our series. So one thing that's a little different than what we've seen before is our terms have an x in it. That's okay, we're just going to treat the x as another constant, only our n is increasing. So it's like we're fixing an x, n's going to increase, and we're going to look at that limit. So in the end, we might have an x in the limit. We'll see what happens. Okay, so let's just go ahead and plug in that information for us. So this means for us, we're going to look at the limit as n goes to infinity of the absolute value of a sub n plus 1. So we're looking at our term a sub n, but using n plus 1 wherever we see n. So that will look like 2 to the n plus 1, x to the n plus 1 over n plus 1 factorial. So now rather than divide by an, I'm going to multiply by the reciprocal of an. So that will look like the following. First, I'll do some color coding here. So there's a sub n plus 1. So now I'm going to multiply by the reciprocal of a sub n. So that would look like n factorial over 2 to the n, x to the n. And that is going to be my reciprocal of a sub n. All right, so let's continue working this out. So we can do a lot of simplification here. So let's notice that we have an x to a power in the numerator and denominator. And we also have a 2 to the power in the numerator and denominator. So we can go ahead and make some cancellations here. So this limit is equal to the limit as n goes to infinity of, so we can see that, change up our colors here, that the 2n in the denominator cancels with 2n in the numerator, but we're still going to be left with a 2 up there. And similarly, the x to the n will cancel to the x to the n in the numerator, but we'll still get an x up there in the numerator as well. And maybe just to carry that one more step, or if we want to not carry it one more step, but rather see it in more detail, what I'm going to do is just rearrange those terms. So 2 to the n plus 1 over 2 to the n. So that takes care of those two terms. Times x to the n plus 1 over x to the n. So that takes care of those two terms. And then I still have n factorial over n plus 1 factorial. So now again, we can see a little bit more clearly how those terms cancel. So 2n with the 2n, leaving us with 2, xn with an xn, leaving us with x. So that becomes equal to the limit as n goes to infinity of 2x times n factorial over n plus 1 factorial. So now we can clean up this n factorial over n plus 1 factorial. So let's just break that down a little bit, each term. So n factorial is just the product 1, 2, 3, all the way to n. And n plus 1 factorial is the product 1, 2, 3, all the way up to n plus 1. So we're going to reach n in that product, but then we'll also have n plus 1. So notice the 1 through n will cancel with the 1 through n in the numerator. So that just becomes the limit as n goes to infinity of 2x times 1 over n plus 1. All right, so notice what is involved in this n here. So we're only looking as n goes to infinity. So 2 and x don't involve the n at all. You can give me an x, I just plug it in there, and it's not varying at all. It's not dealing with the n. So what that means is that we can break up that limit, bring that limit into just that term where we're varying the n. Another thing to notice is that when we have this product here, we're taking the absolute value of it. 2 is always going to be positive. X won't necessarily be positive, so we need to make sure we include absolute value around that x. But since n is going to infinity, we're increasing values of n, so this 1 over n is always going to be positive. Meaning, I can rewrite this as 2 times the absolute value of x, because I want to make sure that x is always positive, times the limit as n goes to infinity of 1 over n plus 1. So I can bring that limit into just the term that's varying, and I can bring that absolute value into just the term that will possibly not be positive. Okay, so what's happening here with this limit? Well, 2 is just going to stay the same. X, absolute value of x is going to stay the same. And we see what happens with this limit. Well, as n goes to infinity, that denominator goes to infinity. So this whole term goes to 0. So if that whole term goes to 0, we have 2 times x times 0, giving us 0. So the limit of the ratios will always be 0. So now let's recall what that implied, or what that ratio test implied if the absolute value of the ratios was 0. Well, you can flip back, or maybe you have a little collection of those convergence tests near you to check. But this means that our series converges. Maybe I won't say that, I'll say so. Our series converges. Okay, so it converges, but for which values of x? Well, it doesn't matter which x I plugged in here. Could I have plugged in 0? Could I have plugged in infinity? Could I have plugged in negative 1/2? Yes, any value of x that I plugged in here, in the end, that limit of this term would go to 0. So 0 times whatever I plugged in for x would still give me 0. So this series actually converges for all values of x. Just to recall, that limit, or to emphasize, the limit that we got in the end doesn't depend on x. So therefore, we always converge in this case for all of x. Now we'll see some examples where this type of behavior doesn't always happen. And it actually depends on which x we use to determine which of these limits converge. And we'll see that in some other examples. But for here, we can just appreciate that this series is pretty nice. I can plug in any x I want to into this series, and it is going to converge for us. All right, thanks for watching.